In this video, we're going to begin to look at the laws of motion. We've already started talking about motion in kinematics, but that was more of a description of the motion. In mechanics, we're going to start to get into more the cause of the motion. The key component that we're adding into dynamics here is the idea of forces and how they act on objects and how the interaction of forces affect an object's motion. The method we are using is called classical mechanics, and classical mechanics is great for everyday situations. However, it starts to break down and it doesn't work in certain conditions. The first condition is when we're talking about very tiny objects. So classical mechanics cannot be applied at the microscopic level. And also objects moving near the speed of light. So when things move really fast, which typically are tiny particles, however, it doesn't have to be. But when objects are moving really fast, some screwy stuff starts to happen, and so classical mechanics once again breaks down. We are not going to get into either of these two in this course. We're just going to deal with classical mechanics of the everyday situation. In this unit, we're going to take a look at Newton's 3 laws of motion and his universal law of gravity. These laws were and still are a big contribution to physics and are considered one of the greatest achievements of the human mind. Before we can talk about Newton's laws, we have to bring in this idea of a force. And forces are commonly imagined as a push or a pull on an object. And it's important to remember that forces are a vector quantity, so they have both a direction and a magnitude. And there's two different types of forces. It can either be a contact force or a field force. And commonly we think of forces as being contact forces, and those aren't tough to think about, but it's the field forces that are a little different, and we're not going to get into very heavily at the beginning of this course. However, later in the course we will talk a little more about field forces. Contact forces result from some physical contact. There's touching involved, so an object pushing another object because their surfaces are touching. Field forces act between disconnected objects, so they act at a distance. Here are some examples of contact forces and field forces. This spring, pulling on this spring, is a contact force because the hand is in contact with the spring. Pulling on this wagon, also a contact force because the hand is in contact with the wagon. Now notice it is up at an angle, and so therefore its direction does matter, and so this vector will have components both in the x direction and the y direction. And then this football is in contact with the push of the foot, and the force once again has both a magnitude and a direction. Now some examples of field forces, and we'll just look at these 3 right here. There are more, but these 3, this one is depicting gravity, in that when we have two masses, they attract because of the gravitational pull, and we'll get into that a little more deeply in this unit. And another one is electrostatic. Two charges that have opposite charges will attract each other because of the electrostatic force, and then this is depicting a magnetic force where we have a magnetic field created by the magnet and it attracts the iron. In this unit, we are going to primarily deal with contact forces. We'll talk a little bit about this field force, and these field forces over here are going to be left for another day. In the world of physics, we do have some fundamental forces, and they're called the strong force, the electromagnetic force, the weak force, and gravity. All of these forces are field forces, and they're listed in order of decreasing strength. So the strong force is the strongest, hence the term strong force, and gravity is the weakest. And you might think that gravity is pretty strong, but actually compared to the other fundamental forces, gravity is very, very weak. And we're only going to talk about gravity and a little bit of the electromagnetic force in mechanics. The other forces will have to be discussed in other courses. Since we're going to talk about this guy's laws a lot, we might as well talk about who is Isaac Newton. Little quick rundown. He was born in the 17th century, did most of his work in the late 17th, early 18th century, and he formulated basic concepts and laws of mechanics. So all of our mechanics, this entire physics course, everything that we do is based off of Newtonian physics, or what Newton discovered about motion. In addition to that, he came up with a universal theory of gravitation. He made many contributions to calculus. He pretty much created the entire idea of calculus, and he also did a lot of work in light and optics. So a lot of what we're going to do in this course comes back to this guy, Isaac Newton. Newton's first law of motion states that when an object that has a velocity, it is going to be constant in magnitude and in direction unless acted upon by a non-zero net force. And the net force here is defined as the vector sum of all the external forces exerted on an object. When we talk about external forces, we're talking about any force that results from the interaction between the object and its environment. So this is going to bring in both the contact and non-contact forces. Internal forces are forces that originate within the object itself, and they cannot change the object's velocity. All of us have internal forces going on inside of our bodies because of the interactions of organs and blood flowing through our bodies, but none of that can create motion in our external body. Only external forces can do that. And so Newton's first law is really the law of inertia. And what we mean by inertia is the tendency to not change. And so an object has inertia. That means that object wants to keep doing what it's already doing. So if it's at rest, it wants to stay at rest. If it's moving at a particular velocity, it wants to keep moving at that particular velocity. And an object that has higher inertia, it has a higher tendency to continue its motion. Let's look at a few different examples here and think through the inertia that's going on. So let's think about a golf ball, hitting a golf ball off of a tee. Initially, the golf ball is at rest, sitting on the tee, and it wants to stay there, and it will continue to stay there until an outside force, an external force, acts on it. So that ball will stay at rest until the golf club hits it. And then that contact force, that force that the club exerts on the ball, will create motion. And then that ball will fly through the air and want to continue in that velocity that it has initially until it eventually hits the ground because of the external force of gravity acting on it. If we were to take gravity out of the equation, that ball would float on forever and ever and ever and would never stop. But because there's an external force, its motion is changing, and then eventually it will hit the ground. Now let's continue with this thought experiment, but instead of a golf ball being on the tee, let's put a bowling ball on the tee and take the exact same swing so we exert the same force. So if we're exerting the same force on a bowling ball as opposed to a golf ball, think about what the difference would be. Would that bowling ball go as far as the golf ball? Well, obviously not. It's going to have a higher tendency to stay at rest. So hitting it with a golf club, it may move it will move it some because there will be an external force, but it's not going to go nearly as far. So we say a bowling ball has more inertia than a golf ball. Both of these objects resist change in their motion. They both have a non-zero inertia. However, the bowling ball has much more inertia and is more likely to resist a change in motion. And so if you think about what are the fundamental differences between a golf ball and a bowling ball other than size, is the mass of the two. And we define mass a little differently than the way you would see it in other sciences. Even though we're still talking about the same thing, we're just focusing on a different aspect of mass. And we say mass is a measure of the resistance of an object to change in its motion due to a force. And so mass is tightly tied into the idea of inertia. An object with more mass is going to have more inertia. Just like the bowling ball has a higher tendency to resist a change in motion because it has more mass than what a golf ball does. Another way we say this is that the larger the mass, the less it accelerates under the action of a given force. This is a very important bridge here in concepts. This is the first time that we take the idea of a kinematic concept in acceleration and we join it with the dynamic concept of force. We will relate those two concepts much more closely later when we talk about Newton's second law, but just keep that in mind that force and acceleration have some type of relationship. Coming back to mass, the SI units of mass are kilograms, and mass is a scalar quantity. There is no direction in mass. It is just a scalar, and we only have a magnitude.